Hello, thank you for watching my presentation today. My name is Kevin Heppner, and I am a process simulation and software development engineer with SysCAD. Today I'm going to be talking about some work we've been doing on modeling the solvent extraction separation of neodymium from praseodymium. In this work, we are using a thermodynamic modeling approach to develop a rigorous model of a rare earths solvent extraction plant. We're going to be talking about what is a process model. Then we're going to look at thermodynamic modeling approaches in SysCAD. Then we're going to look more detail into the solvent extraction modeling within SysCAD. Then we're going to look at the extraction chemistry of neodymium and praseodymium. Following this, we're going to look at model development and validation of this rigorous model for solvent extraction. We're going to do a practical modeling exercise along with some sensitivity analysis, process optimization, after which we will summarize and conclude. So the goal of this work is to demonstrate the capability within SysCAD and thermodynamic modeling to do a first principles model of rare earth solvent extraction. The model we're going to present is relatively simple, but more elements can be required in the same fashion as we demonstrate here today. But what is a process model? We've all heard the term digital twin. Well, digital twin is nothing new. It's been around for a long time. In fact, SysCAD has been around for well over 30 years. And many other simulators are like that as well. Basically, it's a digital twin of your process, which is a process simulation. It's a valuable tool for evaluating what-if scenarios, and it's useful for comparing relative benefits of different operating modes or circuits. A good model will give you good absolute predictions, but its real strength is actually comparison of scenarios. So a comparative analysis is typically more accurate than the absolute values. In all cases, qualitative behavior of a model should be correct, but it should always trend, and it should always trend appropriately with your process. So what constitutes a good model? Well, it needs an appropriate level of detail for what you're trying to do. It should be based on fundamental mechanisms, relevant test work, plant operating data, etc. It's really a container for your process information. It can incorporate all sorts of information like plant data, test work, maintenance records, thermodynamic databases, etc., etc. It has proper documentation without fudge factors, and it can be validated against plant or test work data. A good model responds appropriately to changes in input, and it can be used for a large number of scenarios. Let's look a little bit at how a SysCAD model would be used in the life cycle of an operation. Starting from feasibility all the way through to engineering design, commissioning, plant operation, a SysCAD model can be used. In feasibility, it provides information on mass and energy balances and the process design criteria. As you move into engineering and design and commissioning, it can do things like process control design, dynamic analysis, nameplate capacity validation. You move into a plant operation, it can be used for model predictive control, digital twin, metallurgical accounting. Plant maintenance, it can be used to prioritize work orders by looking at the relative benefits of different process changes that would come from basically doing a work order. Plant expansion, the model then becomes a very useful tool for your EIS, your EA, and it provides stakeholder confidence that you have a very good understanding of what your process does. Then this goes around and around as you continue to improve and change your plant over the life of your plant. So SysCAD can really be a cradle-to-grave solution for your operation. Now, when we say a thermodynamic engine, what are we talking about? Well, a thermodynamic engine by itself is a highly specialized third-party software, and it performs complex chemistry calculations. Typically, these softwares are available to be used directly for single-point calculations. In other words, you provided a composition of your stream that you're interested in, and it tells you the equilibrium composition. This is very useful for understanding particular areas of your plant. However, the advantage of using it as an engine within SysCAD is now you use it right within your process. So you allow incorporation of these calculations into your plant model. You account for recycles and non-ideal effects. Now in SysCAD, capabilities for using these thermodynamic models range from low temperature aqueous solutions to molten metals, eutectics, slags, and high temperature gases. And this is done by the different third-party softwares that we currently support, which includes OLI, FreakC, ChemApp, and EQSol. Now the approach that we take within SysCAD is for maximum flexibility to the user while maintaining computational efficiency. You can do detailed thermodynamics as needed in specific areas of your model while using traditional mass and energy balances elsewhere. Also, you can have multiple types of thermodynamic models on a single flow sheet. So for instance, you could have OLI, EQSol, ChemApp, and FreakC all used in different areas of the process based upon the relative strength of each one of those softwares. So for instance, if you're doing water treatment, perhaps FreakC or OLI. If you're doing brine, perhaps you're doing brine evaporation, perhaps EQSol or OLI. If you're doing smelting, then the choice may be ChemApp. SysCAD has also implemented parallel processing. So this allows you to do very fast computations, and there are user-friendly features to utilize these powerful chemistry analysis tools within your flowsheet. So if we look at a comparative approach, if we look at solvent extraction modeling, isotherm versus thermodynamics. So in an isotherm approach, you would use plant isotherms using production liquor and production organic. Very useful stuff when you have an operating plant. And these are typically done fairly frequently to understand your solvent extraction circuit. However, the applicability is no longer when your operating conditions change. And this, of course, is difficult things to obtain when you're in a design stage and you perhaps only have core samples to understand what your ore might look like. The thermodynamic approach, on the other hand, you generate pure salt isotherms for different components with fresh organic. And this allows you to actually calculate the free energy of formation of the organic species. Because you're using a fundamental approach, they're applicable over a wide operating range. And this is very useful in the design stage. It also sets up the ability to do competitive extraction. So with a good model, you can actually predict your plant isotherms. So this is really the difference. Now, if we look in particular at how we do solvent extraction modeling in SysCAD, we have different layers. So you can do things like specify chemical reactions and extents in your SX model. You can implement plant isotherms, as we mentioned before. And it's able to handle multiple isotherms for multiple metals. So this is a way you could store some of your test work results in your model. And the third way, which we're looking at today, is free energy minimization within SysCAD, either using the FEM module within SysCAD or using a thermodynamic engine. Now, we can incorporate non-ideal effects, and basically you can put a solvent extraction model into your process and have it act as a digital twin of a solvent extraction circuit, of a solvent extraction cell in your actual process. So the workflow we're going to be looking at today, we're going to start with obtaining a pure system isotherm. We're then going to fit that to thermodynamic model to calculate the GF for the species, the free energy of formation. We're going to validate that model against independent data, and then we're going to use the validated model for process design and optimization. Now, I want to acknowledge that the data for this assessment came from the work of Lyon et al., who published a paper in 2017 based on some work that was done at the US Department of Energy. So where we are right now, we're going to start at the beginning. We're going to use some pure system isotherm data available from the Lyon et al. Publication, and then we're going to fit it to a thermodynamic model using the FreakC Pitzer model. So the neodymium praseodymium extraction chemistry is here. Basically, it's extraction by ion exchange of the acid on the organic with either neodymium or praseodymium. Their reactions 1 and 2 are the simple exchange. Reactions 3 and 4 are solvation reactions. So we've included all these 5 reactions. We're going to fit all of these 5 reactions to be able to model solvent extraction. Log K values are calculated for each data fitting, and again, the data was from Lyon et al. In the development of the model, we first modified the Freaksy Pitzer database to include neodymium, praseodymium species and extraction reactions, as well as Pitzer coefficients from various literature sources. The neodymium and praseodymium species were taken from the Lawrence Livermore National Laboratory database that's included with Freaksy. We then prepared a SysCAD model with a single extraction reaction to simulate the shakeout test. Following this, we did a least squares fit to calculate the log K value for each reaction. And after this, we prepared a SysCAD model for rare earth solvent extraction pilot plant and validated the model against the pilot plant. So for the data fitting exercise, we used a Python interface. So SysCAD can be controlled remotely from Python via the COM interface. So basically, we can use some of the optimization libraries within Python to calculate what the log K values are to fit the data. So this is what we did. These are the fitting results. This is for neodymium. With the neodymium varying concentrations, as you can see at the bottom. And praseodymium fitting was also very similar. These shakeout tests are for pure metal chloride salt mixed with a fully acidified cation exchanger diluted in organic carrier phase. And the R-squared of the fit ranged from 95 to 98%. So you can see visually as well as in the R-squared that the data fit was very good. And based on the data fit results, the predominant extraction reactions were the exchange reactions. Solvation did not happen to a significant extent. So it's an exchange of acid with neodymium and praseodymium that was occurring. So we have fitted the data, and now we move on to validating the model against independent data. So here we are, we validated against independent data. The pilot plant experiment done by Lyon et al. Was simulated for each SX unit, and we compared the values against steady state pilot plant data. So the Freaksy model was used as developed without any further modification. So this is an overview of the pilot plant model. So there were 2 extraction stages, 4 scrubbing stages, and 4 stripping stages in the pilot plant. And what we did is we compared them, and you can see the results here. This is the comparison of neodymium to praseodymium. The blue line is the model, and the red dots are the experimental points at steady state. And you can see there's a very good agreement here. And this is for neodymium concentration in the leaving aqueous from each cell. There's a similar story here for praseodymium. Again, there's very good agreement between the model results in the blue line and the actual experimental results, which are the red dots. It's notable that the absolute errors are actually very similar. It's just that the scale of praseodymium is much, much lower. So we validated the model against independent data, and we have a validated model. Now we can use this validated model for process design and optimization. So this is where we are now. So we're going to use it for a what-if scenario. We're going to basically use it to do a sensitivity analysis on a number of operational variables. The sensitivity analysis can identify what variables have the greatest impact on key performance indicators. And this can then feed into decisions for process changes to improve the process. And we can do both design and operating variables, which I'll show you. So this is the model we used for our assessment. We increased the number of extraction cells to 9 extraction cells. So that's what we did here. We also recycled the scrub solution from the scrub process, from the scrub circuit into the extraction circuit to optimize the recovery of neodymium. In scrubbing, we went from 4 cells to 12. We essentially just took the scrub cell and we used the copy and paste functionality within SysCAD to be able to add 2 additional scrubbing cells, and then we appropriately connected them. So within SysCAD, you can take an entire graphic sheet and you can copy and paste it just like in Windows, Control-C, Control-V, and you can create new fully functioning process flow sheets. So that's what we did for scrubbing. And then in stripping, things stayed relatively the same. The only difference is that we tested what would happen if we took some of the scrub solution, or we took some of the loaded strip and recycled a portion of it back to be used as scrub solution. The reason for this is that it has a high neodymium to praseodymium ratio, and it's reasonably acidic. It would help to crowd the organic with neodymium while stripping off the praseodymium. This was the idea. So the results of the sensitivity analysis are found here. Essentially, we did a series of runs from Excel and we controlled the process remotely from Excel. The results here are arranged as an increase in the variable is orange and a decrease in the variable is green relative to the baseline. And there are 4 scrub cells operating. Very briefly, the scrub flow we increased by adjusting the O to A ratio. And the strip flow we also increased by adjusting the O to A ratio in their respective scrubbing and stripping circuits. What you can see is that as you increase the scrubbing flow, the neodymium recovery goes down. As you decrease the scrubbing flow, the neodymium recovery goes up. And of course, as typically you'll see throughout these, is that as the recovery goes down, the rejection goes up. So these seem to be coupled that way. The strip flow, when we increased the strip flow, we had a slight decrease in neodymium recovery, but a slight increase in praseodymium rejection. And this is probably because the strip flow, the loaded strip, portion of it is reused as scrub. So this would increase the acidity of the scrub solution. And we'll see a little bit later that increasing the acidity of the scrub solution has a marked effect on the neodymium recovery and praseodymium rejection. The praseodymium and neodymium feed concentrations acted as you would expect. Increase in praseodymium basically affected the product quality, but it also actually slightly increased the neodymium recovery, likely due to ionic interaction effects. Neodymium feed concentration also had the expected effect. The strip acidity, as you increased the strip acidity, this caused more of the neodymium to be stripped out in the scrub, but it also stripped out more of the praseodymium. So you basically ended up with less recovery and more rejection. And the barren organic concentration, as we reduced the barren organic concentration, what happened there is that basically you end up, if you reduce the barren organic concentration, which is the final column on the right, then what happens is that essentially you crowd your organic with more neodymium because it has a higher affinity, which drops the recovery in this model, but it increases the rejection. So all of these, just as a blanket statement, all of these give trends that are reasonable, but they're also very nonlinear effects. And this is a very simple model. You can see the value of a model like this to be able to predict trends, but you can also really see the value of this model when it is a model of a complete plant operating within a rare earths plant, because you can really start to see what are the effects of these different parameters on your overall circuit. And it's very difficult to model some of these things without a good thermodynamic model. We also looked at design parameter sensitivity. So we looked at neodymium and praseodymium rejection as a function of neodymium recovery and praseodymium rejection as a function of the number of scrub cells. As you can see, as you increase the number of scrub cells, the neodymium recovery doesn't change much, but the praseodymium rejection gets better and better. And this is what you'd expect. So you basically get a more pure product as you have more scrub cells. Now, so here now, let's look at what we did to modify stripping based upon those results. What we did is we took that recycle that part of the loaded strip that we were going to use as a scrub solution, and now we're going to partially neutralize it so that the acidity is less. And so we use sodium hydroxide here, and the results here are preliminary because we're only really considering acid, praseodymium, and neodymium extraction. The extractions associated with saponification are not considered. So because we're adding sodium hydroxide, we're essentially going to have some, albeit probably not a great amount, some extraction of sodium. So these results that I'm showing you are preliminary, but it's just to kind of give you an idea that you can do analysis like this. And of course, if you add the data, then you could get even more information from this model. So in this case, we look at the optimized case with and without sodium hydroxide addition. So without sodium hydroxide addition, basically with sodium hydroxide addition, you end up with higher neodymium recovery, but lower praseodymium rejection. So a very similar story as before. However, trends are realistic. You increase recovery, but you reduce rejection as expected. So to summarize what we've done, the overall workflow is here. We start by obtaining a pure isotherm data. We fit it to a thermodynamic model to calculate the free energy of formation of a species. We validate the model against independent data, and then we use that validated model for process design. So basically, this is the approach that you can take with SysCAD and embedded thermodynamic solvers to be able to do a very rigorous model for solvent extraction. So in conclusion, the results are in good agreement with pilot plant data from Lyon and Udegar. The shakeout test results were fitted to the model with an R-squared between 95 and 98%. The process model matched pilot plant data very well. R-squared of greater than 97% for both neodymium and praseodymium. And the model is extendable to other metals. So you could add, data for cerium, you could add data for yttrium, other metals, provided that you had the similar type of data for the same extractant. And SysCAD can provide these data services given appropriate test work data, or you could do it yourself or anything in between. So once you have a validated model, it can be used for a variety of purposes. Here we showed it for just a simple test to look at a fairly simple model and how you can use it for a sensitivity analysis to understand how it affects the KPIs in your plant. Different levels of accuracy can be incorporated depending on the project stage and the information you have available. And the real power of this kind of a SysCAD model is you can have process model, such as metallurgical test work data, and incorporate it into your model. And the nice thing about doing it in a first principles approach is that it has a wide applicability range. With this, I say thank you. Thank you for watching my presentation today, and I'm open to questions.